Welcome to the third session, which is on Boolean algebra. This session will cover the laws, rules, and theorems that underpin the working of logical systems. You will learn how to define a given circuit using Boolean algebra and expressions and evaluate the way it operates. So, in this session, what do I expect you to know? To understand the basic operations and laws of Boolean algebra, relate these operations and laws to networks and makeup of logic gates, prove any of these laws using truth tables, apply these laws to the manipulation of algebraic expressions. The key topics to be covered are digital systems, logic functions with zeros and ones, truth tables on logic symbols, waveforms, Boolean algebra, properties of Boolean algebra. The recommended test is chapter 2 of Fundamentals of Logic Design. That is where you get most of the materials from to cover that. The basic mathematics needed for the study of logic design of digital systems is based on Boolean algebra. There was a gentleman called George Boole who developed Boolean algebra over 100 years ago and used to solve problems in mathematical logic. Boole's work laid undiscovered for a long time until he did this work over 100 years ago, like I said, but nobody knew its importance until the advent of computers. It's found application in other areas, including set theory, mathematical logic, but we want to look at how it can be applied to switching circuits. So, let's say you have a logic circuit. To this circuit, you have certain inputs and outputs. The task is to determine the binary outputs for each combination of inputs. So, given a task, develop a circuit that accomplishes the task. Of course, there are many possible implementations. One would be to try to develop the best, so to say, circuit based on some criterion, e.g., like, for example, the size, the power, the performance, and so on. So this task looks deceptively simple, because you have just a circuit, a logic circuit, that performs something. And then you have some inputs. So yours is to determine the output for each combination of inputs. And the question is, how do you know that the circuit will perform correctly or is performing correctly for every input? Let's look at a few examples of how these things, can be used. So you have a toll booth controller where there's a barrier gate, on let's say a toll road, where you slot in some money, let's say 1 cedi Ghana coin, and if you slot in this thing, the bar will raise to allow your car to go, and then the gate will then close after you. So for such a logic circuit, you have the 1 cedi as an input. You have the car, the sensor that picks up that the car is present. You have to, then the output is to raise a gate and then to close a gate. So that is what you are supposed to do. The basic operations of logic or Boolean algebra are ones and zeros. Yes. So the basic operations has ones and zeros underlining them. That's and ors. And they are complements, or they are inverse. So these various operations of ones and zeros will correspond to different configurations of the circuit within. Right. So let's say you have a switch. The switch can either be what? Open or closed. If it's open, let's say that's a 0. If it's closed, let's say that's a 1. So if it's open, it means there's no contact. If it's closed, it means there's a contact. So the complement of 0 is 1, the complement of 1 is 0. So you can write this as, 0 complement is 1 or 1 complement is 0. Now, if you have a function, a variable, let's say x, and it's a switching variable, so the complement of x is 1 if x is 0, and the complement of x will be 0 if x is 1. And this will be a basic inventor, something that invents something. So a basic operation you have within logic circuits is to invert. So you change something from 1 to a 0 or from 0 to a 1. And you use that triangular symbol with a small circle at the end to represent an inventor. So you put in x, and at the output you get the complement of x. Now, so the symbol for an inventor is shown, right? You put in an x and you get a complement of x or not x. The truth table is what you see on the top corner. So if the input is 0, then the complement is what? Or you invert it, you get a 1. If the input is 1, you get an output of what? A 0. So this function with the gates that you see, you can represent with a table. And we call this what? The inventor. It's a basic function that you need to be aware of and the way it operates. Now, what about the AND gate? How does it work? So let's take again now, this time, two switches, switch A and switch B. Right. And assume that you have that these switches connect 2 points, 1 and 2. And that at the point 2, you have a lamp. And the point 1, you have, say, a power source. So the question is, you want to switch that lamp at 2 on. Now, what happens? This will only happen when both switches are on. So if A is on and B is on, then the lamp at 2 can be on. Otherwise, it will be off. Okay? So, in other words, when you have A is 0 and B is 0, then the output, that is A and B, will be 0. Remember that you want an output of what? You want the output to be 1. There's a 2 there. If you have a lamp there, that lamp to come on. And this will happen. So if A is not on, that's A is off, B is off, then the output will be off. When A is off and B is on, still it will be 0. And when A is on and B is off, the output will still be off. And then when all of them, A and B, are on, it's only then that you have an output of 1. So the lamp will be on. So the AND gate requires that both switches A and B are on for the thing to be true. So this function is represented by the truth table, A, B, and then the output C. So A and B, A and B is 1 only if the both inputs are 1. How do you represent this? The logic gate for the AND gate is shown, right? So that's your AND gate, and if the two inputs are setted at high, the output will also be high. Otherwise, they are deasserted or 0. Now the OR gate is different. This time, think again of it as having a power source 1, which is connected to a lamp at 2. But the switches A and B are now parallel to each other. So you can have the lamp 2 on if either A is on or B is on. Right? Or both of them are on. The only case where the lamp 2 will be off is when both A and B are off. So we call this the OR gate. So 0 All 0 is 0. 0 or 1 is a 1. 1 or 0 is a 1. 1 and 1 is a 1. So that's an OR gate. And the symbol to represent that is shown. Notice the difference between the two gates, the OR gate and the AND gate. Now, we can use waveforms to describe the circuits. So, if you have an X waveform and a Y waveform, right? Then we can have an X and a Y, or an X and a or we can represent that by these waveforms. So you can study this diagram and see how the two waveforms relate. Now, notice that you can divide this by timing. So you can say, well, the first one ends here. So you get 0 and a 0 is a 0, 0, or a 0 is a 0, and not an X is a 1. So that is high. These are all lows. And then that is a high here, a low there, a low there. So an OR will give you a high, and so forth. Now, the gates you've seen, those logic gates you've seen so far have all been 2 inputs, but you can have more than 2 inputs. You can have 3 inputs, 4 inputs, and so on. So an example of a 3-input OR gate is shown, So again, you can do the truth table for that, where you have A, B, or C as the inputs, and you can then work out the outputs. Something that you must learn is when you have a 3-input, 4-input, you must then know all the possible combinations that you can have. You must be able to write them out for at least up to 4 inputs. 5 will be too much, but you can ask yourselves how many possible combinations are there if you have a 5-input gate. How many possible combinations? And that even pushes it. If it's a 6-input combination, how many possible combinations are there? If it's a 7-input, how many possible combinations, and so on. Now, how do you order Boolean functions? If you have read a function, in what order do you do them? How do you interpret A and B, or C? Do you OR the A and B? Do you first do A and B and OR it with a C, or you do B and C and then end it with an A? So what's the order of precedence? The idea is that you do an AND before an OR. So the AND is equivalent to your multiplication, and OR is equivalent to your addition. If there is any doubt, you can always use a parenthesis or brackets to remove any doubts. Okay? So if you look at the diagram, you have A or B. So this will translate as A or B, and then you end the A or B with a C, for example, if you wanted to remove any doubt. Now, let's look at how to represent A and not B or a C. So we have A, not B, and a C. So if you look at the diagram, that is A, but so you have a B, but you want a not B, so you pass it through an inverter. So the B comes out as a not B, and then you have A and not B coming out, and then you OR that with a C. So you have A, not B, or a C. The same way you can write a function to represent something like that. So this is a C or a D, end that with an A, and then negate all of that, and then all that with a B and an E. Is something that the circuit for that is shown below. You can attempt writing this out. Right, now let's look at the algebra. Now, analyzing these circuits, as they were, can be quite difficult. So there's a way that we should find easier way to sort of manipulate it. So this is where the Boolean algebra comes in. So a Boolean algebra is defined as a closed algebraic system that contains a set of k of 2 or more elements and operators. It's quite useful for identifying and minimizing circuit functionality, and there are a lot of things that you need to know about them, including the identity elements. So if you have, for example, A and 0 will always give you an A and a 1 will give you an A. So that's called what is called the identity elements. So an A or a 0 equals to an A and a 1 equals to an A. You can understand why. So 0 is the identity element for the OR operation, and 1 is the identity element for the what? AND operation. In other words, if you multiply any number by 1, you get the same number. And if you add 0 to any number, you get that number. You still get the same number. So what are the basic theorems? Let's look at them. Operations with zeros and ones. An x or a 0 is an x. An x or a 1 is a 1. Yeah? You can understand why. Because remember, the variables there can either be what? 0 and 1. Yeah? So if you add a 0 to any number, then it should become that number, which is the identity element. And then if you add a 1 to any number, then the answer should be that 1. Because you can only have 0 or 1. And then if you multiply by 1, you get the same number, or if you multiply by 0, then it will be a 0. Then there's another law known as the idempotent laws, where x or an x is an x, and x and an x is an x. There's also the involution law, that is not x, not x, is an x. That is a negation of a negation becomes a positive. Complementarity, laws of complementarity. That is x or not x is a 1. And x and not x is a 0. Again, think about it and understand why these laws as they are. As something for you to do, think of the following circuits, right? Given that A equals to B equals to 0, and C equals to D equals to E equals to 1, write out the output of each gate on the diagram. Yeah. And then also derive a Boolean expression for the circuit output. And then you can then substitute the values to verify your answer. So that brings us to the end of this session. Attempt this question, and we'll continue in the next session to look at further issues on Boolean algebra.